Okay, great. So I hope you guys have seen your free response part of the test. I created a poll in the channel asking you how you did in the exam or what is your score, just to give me a rough idea of how you guys are doing in the class. Um, but generally, how was it? Was Were your scores good, or does it need improvement, or you don't want to talk about it anymore?
Need improvement.
Okay, yeah, that's fine. Because you still have a chance. Because if I remember it right from the syllabus, that you can use your final exam as a replacement for your lowest long test. But hopefully, you'll get better scores in the next exams because so that you can replace the previous exam with the final exam. But again, I already warned you, I guess, last week that um, this chapter might be more difficult than the previous ones, at least for me, because I guess there are a lot of techniques that we need to work on in this chapter, and there's a chance that in the exam you will not be told exactly what method to use for a particular integral problem. So you need to discern on your own what method will work on a particular integral, or what's the most convenient way to solve a certain problem. Okay. So that's another challenge aside from, again, the number of techniques that we need to talk about in this chapter. I guess, Rohel, you want to say something?
Yeah, I just have a quick question. How can we like calculate our grade or see like what our average is in the class right now? Because I think for my college algebra and my pre-calc course,
Mm-hmm.
but like this time, like after the second test, we were like able to see like our grade distribution and like our projected grade. There was a column in
Um,
CASA for it.
yeah, I don't know if that is also the case here that you have a page in CASA that will give you what's your current standing in the class. If there's I'm not familiar with your CASA interface, so if some of your classmates have seen it, can you share it in the chat? But if there's none, then I guess you need to calculate it on your own. I guess tally up all your scores from the quizzes, from the electronic homeworks, electronic quizzes, written homeworks, and then compute it manually using the formula from the syllabus. Right. Unfortunately, I cannot do that as well because I don't have access to all your grades. But yeah, just kindly check the syllabus so you can see the grade distribution. Or maybe you can also suggest to Dr. Almus if she can provide that. I'll send her an email later in the day, and tell her that you want to see a partial tally of her score so far. All right.
Okay,
So
thank you.
you're welcome. Now, so today let's go over some problems from section 8.3, which is trigonometric substitution. Let me share my screen. The thing here is that though we are working with a brand new method, uh, you still need to remember what we did last time about powers of trigonometric functions. Because what we'll do in this particular chapter is to turn an integral that possibly only involves some trigonometric expressions into something that involves trigonometric functions. And if that's the case, then the thing is we might end up integrating a power of trigonometric function or combinations thereof, which means we need to go back and apply what we learned from the previous section into an integral that can pop up in somewhere in our solution in this particular section. So,
We can only see your Microsoft Teams screen share.
oh yeah, I just
Oh, okay.
okay. All right, so let's see. Worksheet number 10. Okay, so here we will have three cases, and again, this method is particularly useful whenever you have radicals in your integral. So specifically integrals of the form a squared minus x squared, a squared plus x squared, and square root of x squared minus a squared. And then the choice of substitution here is basically motivated by the Pythagorean identities. So for instance, for the first bullet, you have root of a squared minus x squared. Oh, by the way, here a is just a real number, right? So for this particular case, the suggested substitution is x equals a sine theta. This is different from the U substitution because here we are changing the algebraic variable x into a trigonometric function, right? But as always, whenever you change the variable, you should also change the differential. So we compute for the differential of both sides to get dx equals a cosine theta d theta, right? So you will replace the dx by a cosine theta d theta. But you might be wondering, why will I change x to a sine theta? Am I not complicating the original expression in this particular substitution, right? But if you do the substitution, you have a root of a squared minus x squared. Then you replace x by a sine theta. So you will basically have a minus a squared sine squared theta over here. Then you can factor out the a squared. You'll be left with 1 minus sine squared theta. And the second factor looks very familiar, or at least it should be, because that's basically involved in the Pythagorean identity, right? So you can have it as square root of a squared cosine squared theta. So your binomial is now a monomial, and another good thing about it, it is a monomial with an exponent 2. So it can go out of the square root function, right? But at the cost of absolute value bars. And here we will adopt a convention that whenever dealing with indefinite integrals, so we can make our lives easier by assuming that here cosine theta is positive, so that you can just replace it with the absolute value of cosine theta. Okay. Again, you can do that, or that would be our agreement or our convention whenever dealing with indefinite integrals. When dealing with definite integrals, it would be a little bit trickier because we need to decide whether the absolute value of cosine theta is positive cosine theta or is it negative cosine theta. And that will depend on the bounds of integration. But again, if we don't have bounds for the integration, then our assumption is that cosine theta is positive, so we can just drop the absolute value bars. Hopefully, we'll have some time later to consider some cases wherein you have bounds of integration, and we need to decide whether to use positive cosine or negative cosine for the square root. Okay. Now this is also the governing principles or governing principle for the next two bullets. You just need to think of what is the applicable trigonometric or Pythagorean identity. So for the second case here, we can let x to be a tangent theta. Okay. So for that particular case, you will use the identity 1 plus tangent squared theta equals secant squared theta. So after doing all the substitutions, this guy will be replaced by a secant squared theta, and you can get rid of the radical, right? And then for the last bullet, here you can let x to be equal to a secant theta. Of course, you need to change dx as well, but the governing identity here is that secant squared theta minus 1 is equal to tangent squared theta. And that makes it easier to remember. If you remember the Pythagorean identity, then you just need to remember what form applies for the target or radical here. So you can choose the right substitution out of this three. Okay. Just a minor caveat. Here we chose x to be equal to a sine theta, but there's nothing preventing you from letting x to be a cosine theta. It's just that you'll have a squared minus a squared times 1 minus cosine squared over here, which would be cosine squared, which would be or sorry, you'll have a 1 minus cosine squared, which will be sine squared. So here you will end up with an a sine theta. So yeah, so what I'm trying to say is here you can instead use a cosine theta. Here you could also choose a cotangent theta, and here you can also choose a cosecant theta. But I guess these are the common choice or the common choices for the substitution. But again, nothing is preventing you from choosing their corresponding trigonometric partners. Okay. But of course, before doing this, you might be, I guess this is one of the easiest technique of integration to spot because you just look at the problem. If it has a radical, then chances are trigonometric substitution would be a nice candidate for the solution for that particular problem. But just try U substitution first because that might work, or compare it with the usual integration formulas that you already knew, because so that you will save time. For instance, if you look at the exercises here, you might be tempted to use trigonometric sub once you saw number 1 because it has a radical there. You will get the right answer, but you should recognize that this is an elementary form, right? We have a formula for the integral of 1 over 9 minus x squared in the form of arc sine of x, right? Also here for number 2, you could use trigonometric substitution. Now, nothing is wrong about that, but that will be longer than what will happen if you will use U substitution, because here you can simply choose U to be equal to 9 minus x squared, then the U would be a negative 2x dx, and then you should be good, right? So here, this is an integral formula. Here you can use U substitution, and then you will be good. But again, using trigonometric substitution will give you an equivalent answer. But of course, that will take longer. But I guess the first challenge for this set of exercises would be problem number 3. So let's start with this relatively easy example. Okay. It's a little bit uneasy for me right now because I cannot see the chat. So I don't know if somebody's asking a question. Can somebody monitor the chat? I mean, when somebody asks a question, can you unmute? Can somebody unmute him or herself so that to call my attention? Because I cannot see the chat while on my note-taking app. Let me see if my.
Yeah, no one said anything yet.
Okay, thank you. Just let me know if somebody is sending some questions over there. But okay, let's try this relatively easy question, and then let's try to move on to more complex ones later. Okay, so here U substitution will not work because your candidate for U is 9 minus x squared. Du would be negative 2x dx. You can get the 2x dx from the top, but that will leave you with an extra x. And if you have an extra x, then you will have a square root. That will entail a square root substitution with U involved, right? So that means that will be of no help. So let's go trigonometric substitution here and look at the form here. So we have 9 minus x squared. So that means this begs the use of the sine and cosine Pythagorean identity. So I will let x to be equal to 3 sine theta. Okay. But again, when you change the variable, you should also change the differential. So that means dx is equal to 3 cosine theta d theta. Okay. And so what will happen now is that, okay, we'll have an integral. X squared will be replaced by 3 sine theta quantity squared. Then here we'll have 9 minus 9 sine squared theta. Right? And then dx is replaced by 3 cosine theta d theta. So that's the second step. First, you choose your trigonometric substitution. And second, employ the trigonometric substitution by changing all the variables in the original integral into the variable theta. All right. And then the next step is to try to simplify and see if we can make the integrand simpler. So we'll have a 3 squared, that's 9, then a 3, so I'll have, I guess, a 27 outside. And then I'll have a sine squared theta, cosine theta, all over. And then in the denominator, I can factor out the 9. I'll have a 1 minus sine squared theta inside the radical, and then d theta, okay? And then I can take a 9 out of the square root there. So I'll have 27 over 3, so that's going to be 9. Then square root of sine squared theta, cosine theta, all over cosine theta, e theta, right? And then I can cancel the cosines and be left with 9 integral of sine squared theta, d theta. And this is what I'm saying earlier, that since we are doing trigonometric substitution, there's a big chance that the resulting integral will require integrating powers of trig functions. And true enough, that's what we have here. We have an even power for sine. Remember what we do when we have even powers of sines? We use the half angle identity, right? So this is 9. I'll write sine squared as 1 minus cosine 2 theta all over 2 d theta. So this would be 9 halves integral of 1 minus cosine 2 theta d theta. And then for this, I will need to let u to be equal to 2 theta, so that du is equal to 2 d theta, or du over 2 is equal to d theta. So basically, this becomes 9 halves integral of 1 minus cosine u, and then d theta is du over 2. So this would be 9/4 integral of 1 minus cosine u du, which is now easy to integrate. It will just be 1/4 of u minus sine u plus the arbitrary constant c. Let's go back to the variable theta. So that's going to be 9/4 of theta, or sorry, of 2 theta. Minus sine of 2 theta plus the arbitrary constant c. Okay. And now we need to go back to the variable x. So remember that we let x to be equal to 3. Was that 3? Yeah, it's 3 sine theta, or sine theta is equal to x over 3. That means theta is arc sine of x over 3. Okay, so you can use this substitution, this statement here, to change your theta there. Also, you could choose to change your theta, or your sine, or your theta inside the sine, in terms of the arc sine function. But that will make your integral look complicated, and it will look messy, especially if you will be dealing with definite integrals later. That's why instead of just putting in theta equals arc sine x over 3 inside a trig function, we want to see what is that trig function equal to, right? And we will draw a triangle to find exactly what sine 2 theta is equal to, right? So, but for that, I will need to write it first as 9/4 of 2 theta minus 2 sine theta cosine theta. That's a trig identity over there. So this was replaced by this guy by a trig identity. And then let's see what sine theta and cosine theta are in terms of the variable x. I'll use this substitution statement. Remember that here. From there, I can discern that from SOHCAHTOA that x is the opposite measurement from theta, and 3 is the hypotenuse, right? SOHCAHTOA. So you draw a triangle, a right triangle. Say the right angle is here. Choose where you want to put theta. I'll put theta over here. Okay. And then from our statement here, opposite theta should be x units. The hypotenuse should be 3 units. So that means the third side by the Pythagorean identity is 9 minus x squared. Okay. So now I can compute this expression. I have the 9/4 here, 2 theta, but we knew that theta is arcsine of x over 3 minus twice of sine theta cosine theta. So we knew that sine theta is x over 3. But what is cosine theta? Cosine theta, remember, is adjacent over hypotenuse, adjacent to theta. So theta is here. Adjacent to it is the root of 9 minus x squared over hypotenuse, which is 3, right? So that means this will have root of 9 minus x squared all over 3. So then we can have it as 9/2. I'll factor out the 2 in front of the 2 terms there. So I'll have arcsine of x over 3. And then we'll have minus x root of 9 minus x squared all over 9 plus the constant c. I forgot the constant c here. Just insert that. All right, and that's it. That's the answer to your integral. So this form is particularly more pleasing to the eye instead of this guy being written as sine of 2 arcsine of x over 3. Though, well, actually, this is not too bad in itself, but I guess it's more elegant to have it written this way rather than this, which involves a lot more complicated the more complicated arcsine function. Okay. Okay. Is the method is the process clear? Is this okay? I have a question. Do you want to go with some more basic stuff, or you want to go with some harder problems?
Can we do one more basic?
So one more basic? Okay,
Yeah.
fine. Yeah, that's fine. Because I understand that I was thinking that this problem is basic, but when I started doing the solution, it is not that easy, right? But I guess this is the most basic one I can find from just looking at the problem. So let's see. So I want you to learn the process at least from what we are doing today, so that you can try to answer the more complicated ones. When I say more complicated ones, that are just some longer uh, uh, solutions that will require longer substitutions or longer solutions per se. So I hope you'll get the process from our session today. So let's try problem 6. Okay. So the integral of x cubed all over x squared minus 9. Is it a good example with trigonometric substitution? Because I'm trying to see if I can use U substitution. Oh yeah, I guess here I can do U substitution. Let me just try. Because there's no point in choosing a complicated method when a simple U substitution will work. But again, it's very tempting to tackle it in terms of trigonometric substitution right away, right? But if we let u to be equal to x squared minus 9, then du will be equal to 2x dx. And then I can write the integral as x squared times x dx all over root of x squared minus 9. And if I do the substitution, from here I knew that du over 2 is the replacement for x dx. And then x squared is just u plus 9 all over u to the 1/2 times du over 2. So I guess problem number 6 is not a good example of using trigonometric substitution, because you can solve it using the usual U substitution. actually earlier I started doing it using U substitution, which is still fine. You will have a bunch of secants there, but I guess you will have secant to the fourth somewhere in the solution. Actually, no, I think I did a mistake there. But anyway, yeah, you can use trigonometric substitution still, but that will be much longer, right? So again, I suggest you try U substitution first. So let's not include this because you can use this. You can solve this using U substitution. Let me see. Let me choose another one. Let's try. Let's see. Let's try problem 16. Oh, though this is still an arc sine, but hold on. Let me see if there is a similar problem. Okay, maybe I'll try 23 instead. Because this is again an arc sine or a sine substitution, but we just did an arc sine substitution. So let's try 23. At first look, problem number 23 seems to be out of form for trigonometric substitution. But one technique that we can do is to rewrite the denominator using completing the squares. Because if you look at the denominator or the radicand, you get x squared minus 2x plus 5, right? But I can group them into two, okay, and write it this way. And then I will be looking for the completing term for this binomial, right? So if you remember completing the square, you take half of the middle term. So the middle term is 2x, or sorry, just take the coefficient of x, take half of it, so half is 1, square that, so that means the completing term is 1. So we put the 1 here, but since we placed the 1 there, I need to subtract 1 from it. So here I can look at that given expression as x squared minus 2x plus 1 plus 4, right? You can simplify this to verify that it is indeed equal to the original radicand. But the nice thing about this form is I can factor the first group as x minus 1 quantity squared plus 4. So that means I can write the original integral as dx over root of x minus 1 squared plus 4. And at this particular point, I can do a simple U substitution. I can let U to be equal to x minus 1. That means du is equal to dx. That means here I'll have a du over root of u squared plus 4. Okay. But we don't have a formula yet for this kind of integral. You have the arctan if you don't have a square root in the denominator, but we do have it. Another U substitution will not help us here. So I guess the only recourse we have is to use trigonometric substitution. And for that, we need to let, again, we want u squared plus 4 to be a trigonometric function. And the identity that we'll use is that tangent squared theta plus 1 equals secant squared theta. So here I will let u to be equal to 2 tangent theta, right? So that means du is equal to 2 secant squared theta d theta. So we replace the u's appropriately. So du is 2 secant squared theta d theta all over root of 2 tangent squared theta. Oh, sorry, that's a 4 because that's u squared plus 4. And then this would be what? 2 secant squared theta d theta We factor out the 4, and then we'll have a tangent squared theta plus 1 left in the denominator. Then we'll have 2 secant squared theta d theta all over 2 square root of secant squared theta. And then this is just secant squared theta d theta all over secant theta. Again, our convention, we assume that secant theta is positive. That's fine because it's an indefinite integral. And then we can cancel, so this will just be the integral of secant theta d theta. And remember the integral for secant theta. The integral for secant theta, we have a formula for that already. It's secant theta plus tangent theta. Right? So that means this is ln of secant theta plus tangent theta plus the arbitrary constant c. Now we need to do step-by-step reversion to the variable x, but recall on the side that earlier we let u to be equal to 2 tangent theta, right? Let me see. Yeah, we let u equals 2 tangent theta. So that means tangent theta is equal to u over 2. And from your high school SOHCAHTOA, tangent is opposite over adjacent. So draw a right triangle. Say the right angle is here. Suppose theta is over here. Opposite theta should be u units, and adjacent to theta should be 2 units. And on the hypotenuse should be u squared plus 4 units, or the root of that. Okay? Now, from there, I can solve for secant theta. Secant theta is the reciprocal of cosine, so this should be hypotenuse over adjacent. So the hypotenuse is root of u squared plus 4. Adjacent to theta is 2 units, so that would be our secant theta. So we'll have ln of secant theta, root of u squared plus 4 all over 2, plus tangent theta. Tangent theta is u over 2, plus the arbitrary constant c. And then we need to go back to x again. Remember, u is what? U is x minus 1 plus 4 all over 2 plus x minus 1 all over 2 plus the arbitrary constant c. Or you can also simplify the radical. So this would be root of x squared minus 2x plus 5 all over 2 plus x minus 1 over 2 plus c. And that's our final answer. Okay, is that good? Or did I go very fast? Any questions, clarifications? Any comments?
Very fast.
Okay, but is there any part of the solution that doesn't make sense? Aside from my doing it a bit faster this time? So let me just outline the solution for you. Let's see. Okay, first is we need to decide whether we really need trigonometric substitution or can we apply trigonometric substitution. And to have that, I need to complete the square over here. I guess that's the additional step here. Sorry, compared to the previous problem. This is something that you have encountered in pre-calculus already. So I rewrote x squared minus 2x plus 5 in terms of this guy, which I want because I can let u to be equal to x minus 1. Sorry again. So the denominator will have the square root of u squared plus 4. Okay. And then from there, I can compare it with the 3 cases that we have earlier. And we see from there that we can do trigonometric substitution letting u to be equal to 2 tangent theta. Okay. But once you have decided on the trigonometric identity, you need to compute the change of differential. Okay. Then once you have that, you change all your variables to the new trigonometric variable theta. So du now becomes secant squared or 2 secant squared theta. And then do also the substitution in the denominator. Then perform some simplifications until you come up with the simplest form for the integral. And now from here, you're on your own. You need to figure out how to evaluate that simplified integral, but hopefully that integral is much simpler than what you started with. And chances are there would be a lot of trig functions over here. But luckily, after simplification, we see that the integrand is just reduced to secant theta. And thankfully, there is a formula for that. The integral of secant theta is ln of secant theta plus tangent theta. So I do the reversion to the original variable step by step. And for that, I need a sort of the use of SOHCAHTOA over a triangle here. So go back to your U substitution, see what the trigonometric function is equal to, and then recall from SOHCAHTOA that tangent is opposite over adjacent. Draw a triangle, decide where to put the right angle and where to put theta. Okay, and then once you chose the position of theta from your U substitution, put the appropriate quantities. So for instance, tangent theta is u over 2, so opposite theta should be u units, and adjacent to theta should be 2 units. And then the hypotenuse, use Pythagorean identity. And then you can find what those trig functions are equal to. All right. So I know it requires a lot of practice to get used to this type of substitution. It's not we don't see this often, especially in exams, because this is quite long. But I don't know what will happen to your exam. But yeah, you need to do a lot more practice for problems like these. Let's try another one. Let's try, say, let's see. Do you see anything interesting from these problems? Maybe let's try problem 22. I guess this is similar from, it's similar with one of the problems in the electronic quizzes. So probably you guys have encountered this before. There are several ways on how to solve this problem. Let me see which one should I do. Well, I'll do U substitution first, just to make it cleaner to the eyes. So here, I can try letting U to be equal to e to the x first, okay? And that means I will need the du equal to e to the x dx, right? But I don't have e to the x in the numerator. So what I'll try to do is to force the issue that I have an e to the x dx over there, but I need to cancel it with an e to the x below so that everything simplifies back to the original expression. And then the denominator originally has an e to the x and the square root of e to the 2x plus 4, right? So when you simplify this expression over here, that will we will go back to the original problem, right? Again, the only reason why I want to write this expression this way is so that e to the x will be replaced by du. Then in the denominator, we'll have, this is u, this is another u, so we'll have a u squared times the root of u squared plus 4. Okay. Now, for this particular integral now in the variable u, a u or w substitution won't work. So I will need trigonometric substitution here. I will let u to be equal to 2 tangent theta. I think that's the same substitution we used before, but anyway. So then that means du is 2 secant squared theta d theta. Okay. And then what else? I guess that's it. Aside from having u squared equals 4 tangent squared theta. Okay. Now let's replace all of the u's with the thetas, right? So du will be replaced by 2 secant squared theta d theta. U squared is 4 tangent squared theta, so that goes there, and also inside the square root. Okay, everything's fine up to this point. Okay, I hope the process is making sense. Of course, understanding the process might be a little different from actually knowing how to solve this or the ease of doing the calculations. So I hope for today you will learn and understand the process so that you can try to answer some of the exercises later on your own. So you get your hands dirty and you get used to doing this type of calculations. Okay, because I don't think there's an easy way to really master this particular section, but to try as many problems as possible. All right. So practice, practice, and practice. Math is not a spectator's game. You need to get your hands dirty by answering some problems. If you struggle, that's fine. That's why we are having these lab classes so that you can answer questions whenever you encounter difficult problems. Okay. Okay, so let me continue. I can have it as 1/2 integral of secant squared theta d theta over tangent squared theta. Then we'll have the square root of 4 times tangent squared theta plus 1. Okay. And then there we can apply the identity. So we'll have 1/2 root of secant squared theta d theta all over tangent squared theta. And then 4 will come out of the radical as a 2. And then we'll have square root of secant squared theta in the denominator. So ultimately, we'll have 1/4 integral of secant squared theta d theta all over tangent squared theta times secant theta. All right. And then let's further simplify and see what integral we will end up with. So we can cancel one of the secants from top and bottom. We got this all over tangent squared theta. All right. Now, we don't have a trig power of this form. So let me try applying a couple more trigonometric identities here. Remember that secant theta is 1 over cosine theta. So instead of a secant on top, I can have a cosine in the denominator. And tangent squared theta is sine squared theta over cosine squared theta. So I should have had a longer integral sign there and a 1/4 in the middle. Okay. And here I can cancel this cosine with one of the cosines there. So we'll have 1/4 integral of d theta all over sine squared theta all over cosine theta. Or better yet, write it as 1/4 integral of cosine theta d theta all over sine squared theta. Okay? And at this particular point, I can let w be equal to sine theta. So dw then would be cosine theta d theta. So now we'll have 1/4 integral of dw over w squared. That's going to be 1/4 w to the -1 all over -1 plus the arbitrary constant c. Or that's -1 over 4w plus c. And then we need to go back to the original variable, theta. So this would be -1/4 sine theta plus arbitrary constant c. But remember, we have the variable x, so we need to draw a triangle here. Say the right angle is here, theta is over here, and then review the U substitution, the trigonometric substitution that we used. What did we use? We let U be equal to 2 tan theta. So U equals 2 tangent theta. Okay. Let me put it here. That means tangent theta is equal to U over 2. And tangent from SOHCAHTOA is opposite over adjacent. So if theta is over here, opposite it should be U units, and adjacent to it should be 2 units. And the hypotenuse would be U squared plus 4. Okay? So sine theta then would be equal to, okay, we have -1 over 4 sine theta. But sine theta is opposite over hypotenuse. So all opposite theta is U units. The hypotenuse is the root of U squared plus 4. There's a 1 there, plus C. All right. Any questions?
We have to convert U to e to x, right?
Mm-hmm. Yeah, I need to go back because our original variable is x. So because here I got 3 layers, right? I went from x to u to theta and then to w. So yeah, 3 substitutions here. But anyway, let's carry on. So this is a negative root of u squared plus 4 over 4u plus c. But you're right. We let u to be equal to what? E to the x? Let me see. Yeah, u is e to x. It's minus e to the 2x plus 4 all over 4 e raised to x plus c. Okay. The final answer doesn't look that complicated. It doesn't look bad at all, but you see the pain that we went through in order to get to this final answer. So, yeah. So you see how long solutions can get whenever using trigonometric substitution. So you try to avoid the trigonometric substitution as much as possible, but there are really some instances that the only way to go is trigonometric substitution. And for that, be prepared to deal with lots of trigonometric functions. And for that, you need to remember how to integrate powers of trig functions. That is section 8.2. Plus to remember the at least the basic identities from algebra or pre-calculus. All right. And again, I think you already realized that you need to practice a lot in order to get the hang of it. Theoretically, the process is straightforward. You got these radicals. For certain forms of radicals, you have the appropriate U substitution. But practicing it or carrying out those calculations is another thing because there are several layers that you need to go through. You might encounter U substitution in the middle. You might encounter powers of trig functions in the middle. So you need to be a little bit careful and not to get lost into the process. So yeah. So I guess the thing here is that this worksheet includes a lot more exercises. We only answered, I think, 3 or 4 problems today. So you have lots of exercises here to practice with. This is from the textbook. So if you go to the textbook, the answers to the odd numbered problems are there. So you can check yourself right away after doing it. You'll see the final answers in the textbook. I'm not sure if the textbook also have the detailed solution, but at least they have the final answer, I'm sure. And then if you encountered some difficulties with some of the problems here, let me know on Wednesday so we can talk about them. And even if you have encountered some difficult problems from the quizzes or the homeworks, then just let me know. All right. Oh, by the way, I don't remember if I mentioned it when we started that if you have questions with how the exam was graded or the free response part was graded, if you have questions about why you got too many points taken off for a particular problem, if you feel you got the right answer, or if you think you merit a higher partial credit on a certain problem, just let me know. Send me a chat or an email, and attach to it the PDF file of your graded free response part. Then type in your questions in the body of the email or chat, and then yeah, I'll take a look at it, and then we'll try to resolve it and see if I can give you more points to it. Because the thing is, I might not be the one who graded certain parts of your exam. We did it randomly among us, the TAs. So let me know. I guess there's a deadline. I'm not sure when the deadline is. I just forgot, but I guess it's Friday if I'm not mistaken. I'll announce it again on Wednesday, but let me know until Friday if you have some questions. After that, we will not entertain any other corrections. Okay, guys? So practice, practice, practice. Let me know on Wednesday if you have some questions, all right? Okay, let's call it the day right here. Thank you for coming today. Enjoy the rest of the day. Again, practice, practice, practice. And let's see each other again on Wednesday.
Okay, what's your email?
Oh, okay. I can write it here. Hold on. That's edu.edu.ph. That's my other work email. But I guess if you go on to my display picture in Teams, you'll see a button there to send me an email. That also works, or send me a chat. So this is an alternative way of contacting me. Okay. So either way is fine with me. You can contact me through any means.
Thank you.
All right. Okay. Bye, everybody.